Hello viewers and welcome to another episode of Space Science with Python. Today we are talking about the comet 67P Churyumov-Gerasimenko, and we will see how or if Jupiter had an influence in the past on this comet and altered its orbital elements. And you may remember a few weeks ago, a few months ago, we already did that in the, I think, a sphere of influence of Earth for an asteroid. And I will provide the link into the description where we already talked about the concept, how we can determine how, if an object is altering the orbital elements or the dynamics of another smaller object. So without any numerical numerical simulation or so, just with a simple analytical approach. And last time we talked about Churyumov-Gerasimenko and we took a look at the spice kernels. And we saw that in the spice kernels, the orbital elements are changing over time. And of course, if you take the orbital elements from, for example, the minor planet center, then you see or you get, let's say, only steady state results. So they're not changing at all. And in this video today, we are checking whether or how Jupiter had an influence in the past. But before we dive into this, let's talk a little bit about the theoretical concept that we are tackling today. And again, I did a first smaller video a few months ago when I started this video series, but I was thinking to make a small recap with this very well-known comet that was visited by the Rosetta spacecraft and the lander Philae. Now, first of all, let's draw the sun. And the sun is here in the middle, so a very nice yellow dot. We have also the planet Jupiter. Let's take this color here. And Jupiter is, for example, somewhere here. At the distance, it's around 5 AU, so 5 times the distance between the sun and the Earth. So the Earth would be, let's guess, somewhere here. But let's get rid of the Earth in our case, and let's draw in our comet in a second. So as we talked in the past, each object has, of course, a gravitational pull. So each object, the sun, Jupiter, and so on, they attract, of course, bodies or anything. Of course, any mass in the in the universe has a gravitational attraction. So it doesn't matter what size these objects have. So if we want to compute the movement of all objects, also with all minor planets, so let's draw in some asteroids in here or comets or whatsoever, everything is linked with each other. So they have all gravitational influence to each other. Yes, so it's a little bit complex and, of course, in a very heavy numerical computation. But this is a little bit chaotic. This is beyond our scope. So maybe in the future we will do this. And also for this kind of simulations, Python is not the first choice because Python is for this heavy numerical simulations, quite slow and not very efficient. So how can we do this? So if we reduce our problem to a two-body problem, then of course we take maybe only the sun in the center and ignore everything else. So if we draw in again our small comet somewhere here, then we only care about the interaction of the comet with the sun, and we neglect the mass of the comet because the sun's mass is way larger. So it's a simple two-body problem, and we get some kind of orbit of the object revolving around the sun. And in the reference frame, we talked about it in the past and also with the corresponding orbital elements. But in our case, we will do it a little bit differently because each object, if there's some astrodynamical concept called sphere of influence, where we say, okay, within a certain sphere about larger objects, so let's draw it here for Jupiter. Within this sphere, we neglect the gravitational pull by other objects, like, for example, the sun, and we are then completely Jupiter-centric. So we don't care about the gravitational pull by Saturn or the Earth or Mars or the Sun. We simply concentrate on Jupiter. And well, the so-called sphere of influence has a diameter of, I think, something like 0.3 AU. So around 50 million kilometers. So within this sphere of influence, we are neglecting any gravitational pull, the SOI. Now let's clean it up a little bit. And let's draw in our comet and how we will proceed today to determine the gravitational effects of Jupiter on our comet 67P Churyumov-Gerasimenko. Now, Churyumov-Gerasimenko, it's revolving around the sun. It's sometimes here, then it's moving here, and then here. So it's making its orbit. I should maybe make it more clear that it's some kind of elliptical orbit. Let's see, something like, maybe it's something like here, flying here, flying here. And at some point, it may intersect the sphere of influence of Jupiter. Now, at this particular point where the comet is intersecting the sphere of influence, we are switching the coordinate systems. So we are leaving our sun-centric coordinate system and switch to a Jupiter-centric coordinate system. And within this Jupiter-centric coordinate system, we are computing the orbital elements of Churyumov-Gerasimenko and see how the trajectory of the comet is within the SOI. So we see how it continues moving. So let's see, it moves like this maybe, until it reaches again the sphere of influence of Jupiter. And then at this second point, so this is like our first contact point, this is our second contact point. At this particular contact point, we are then switching back to a sun-centric coordinate system and compare the orbital elements at position 1 with the ones from position 2. So let's see if, for example, the set of orbital elements 1 is equal or not to the orbital elements at position 2. Small spoiler, they're not. So we can see or determine the gravitational influence of Jupiter on comets, or in this particular case, Churyumov-Gerasimenko, and we can determine how Jupiter's gravitational pull is changing the orbital elements of Churyumov-Gerasimenko. So that's all about the theory, and now let's dive into the code that I prepared and already uploaded on GitHub for you. So of course, in the beginning, we need SPICE and some modules, of course. We compute the gravitational parameter times the mass of the sun and also of Jupiter in cell number 2. And then in cell number 3, we are computing determine the orbital elements of Jupiter. And we do this by first computing any random state vector of Jupiter. So remember, a state vector is a 6-dimensional vector that contains the position x, y, z in a certain reference frame, here in the sun-centric ecliptical coordinate system, as well as the velocity components vx, vy, and vz. And this state vector is then being put into another SPICE function called oscaldx that converts the state vector into the corresponding orbital elements. And what do we need here, or why are we doing this? Well, I would like to extract the semi-major axis at this point, where it shows us it's 5.2 AU. So let's simply execute it. And then we can compute the sphere of influence of Jupiter by computing the semi-major axis times the mass of Jupiter divided by the mass of Sun. In our case, we have G times M of Jupiter and the Sun, to the power of 2/5. So this provides us the radius. This is like an approximation of the sphere of influence. And then we convert it from kilometers to AU just to make it more human readable. This is done now here in cell 4. And then we see it's 0.3 AU. This is our preparation. And now in the next step, we are then also doing the same thing for the comet itself. So for comet 67P, we have here the SPICE function spkgeo, the target, the NIF code that corresponds to the comet, some initial time. I just picked up 2004, the reference frame, and the sun in the center of our computation, computing the state vector, determining the corresponding orbital elements. Now, this is something we will store now and use later. Now, I would suggest to find the intersection between the comet and the sphere of influence of Jupiter. And you see here, this is a different date than this one here. Yeah, I just tried out some dates and wanted to see when the comet is intersecting or entering the sphere of influence of Jupiter. So I just adjusted the year a little bit to reduce the computation time. And what we do here in cell number 6 is that we are computing now the time when the comet enters the sphere of influence of Jupiter. So while the comet, the distance between Jupiter and comet is larger than the radius of the sphere of influence, do the following code. And the following code is quite simple. In 1 hour steps, the state vector of Churyumov-Gerasimenko is being computed, and then we check here the distance between the state vector of Jupiter and the comet to determine the distance, and then we see if this distance is larger or smaller than the sphere of influence. And this is how we do it here based on our orbital elements. So we're not using SPICE, we use the orbital elements in our case. So this is cell number 6. And then in cell number 7, it's already being executed. We see the date when the 67P is entering Jupiter's sphere of influence. So in our case, it's the 20th May of 2018, and the distance corresponds perfectly to the radius of the SOI. Now what we need to do now is we need to switch the coordinate systems, and this is simply being done by a switch of, or just by simple vector computation. So let's execute this cell here, this cell number 8, and let's take a quick look what we are doing. So let's get rid of some of the information here. Yeah, maybe I shouldn't have deleted this one, but it doesn't matter. Let's redraw our SOI and our comet at the time when it enters the sphere of influence. So we have 2 vectors, of course. The first one is the vector between the Sun and Jupiter, this one here, and we have the vector between the Sun and the comet. And what we need now is the vector here. Let's draw it in red, from Jupiter to the comet. So what we do is, we use this vector here, from Jupiter to the Sun. So simply inverting the elements to here, and this is how we get our vector. So minus the vector of the Jupiter state vector plus the vector of our comet. And this is being done in cell number 8, so you see it here. And then we compute the corresponding orbital elements with respect to Jupiter. So this is important here because we use now the orbital elements to compute the state vector of the comet within the sphere of influence. Let's take a look at some statistics. Well, the closest distance between the comet and Jupiter is what we see here. It's around 41 million kilometers, and so that corresponds to 86% of the radius of the SOI. So it's quite in the outer regions of the SOI, and the eccentricity in the Jupiter-centric coordinate system is 8.6. So a very hyperbolic orbit, and this is what we expect, right? The comet is entering the SOI and leaving at some point, so it shouldn't be bound to the planet itself. Now what we do now here in cell number 10, the same thing that we did in cell number 6. We are computing the state vector of the comet within the sphere of influence as long as the distance between the comet and Jupiter is smaller than the sphere of influence. And for the state vector, we are using the orbital elements within the Jupiter within the Jupiter system and compute it and compute the distance between the comet and Jupiter by simply taking the norm of the state vector itself, or the first three components x, y, and z. So basically what we do now here is, as I said in the beginning, we are the orbit up. Now, come on. The comet is now flying here through the SOI, which looks like this. So we have here maybe in there. Now this is a very extreme case, of course. And then we are computing the state vector in this direction, and so on. And the length of this not the state vector, but the positional vector is, of course, the distance here needs to be smaller than the SOI, otherwise it crosses the SOI, and then we have to switch back to a heliocentric coordinate system. So this is quite simple. We do this also here in this while loop, as I just said, and then we can see when the comet is leaving the SOI, and in this case it's now it's now it's cell number 11. It's leaving the SOI at the 20th of May 2018. So let's see, when did it enter? And I just saw that I made a small mistake. I didn't execute the while loop, so that's why I got the same date. And I was a little bit confused why it's the same date. It's the comet's not that fast in the SOI, so yeah, I had to execute this cell here, and it now makes sense. It's the 9th of September, so the comet was within the SOI for around 4 months. Okay, pretty nice. So now we are at the SOI, so the comet is leaving the gravitational influence of Jupiter. And now we can compute the state vector of Jupiter and recompute our state vector of the comet in heliocentric coordinates. This is being done in cell number 12 now. And then afterwards, we can simply calculate also the corresponding orbital elements in cell number 13. And in cell number 14, we are then computing the orbital elements before entering the SOI and then after leaving the SOI. And this is now being done in the very last cell, where we have here the perihelion, eccentricity, inclination, longitude of ascending node, the argument of perihelion. And this is what we do now. And we see that we have small changes in the orbit of Churyumov-Gerasimenko in heliocentric coordinates. So for example, the perihelion decreased by 0.07 AU, the eccentricity increased, so it became a little bit more elliptic. The inclination, the comet was forced more into the direction of the ecliptic plane. And also the longitude of ascending node and the argument of perihelion changed by a few degrees. So you see, without any heavy numerical computations or calculations, we were able to see how Jupiter influenced the orbital elements of this particular comet in our solar system. And you can redo these calculations for actually all asteroids or comets and all SOIs of all planets. But then again, it becomes a little bit computational heavy, and you are entering some kind of simple n-body simulation. So if you do this, you can also start creating an n-body simulator, maybe written in C or C++, so which is then more efficient and faster than Python. But of course, you're encouraged to learn these things and do it as well. But this is something I wanted to show you now in the last video and today, how the SPICE kernels and also have changing orbital elements, and how this can be explained by the gravitational influence of our larger gas giant, namely Jupiter. Very well, so this is another video number 25 of our, let's call it, general space science with Python tutorial session. And as I promised, in the future, we will dive into the near Earth object project, I'm still preparing it a little bit. So in the meantime, I will just create some new general space science tutorials. So I hope you have the patience for waiting for the next project. And until then, I wish you happy coding. Again, just write me your comments and ideas or so. I mean, sometimes I get some very nice ideas and also questions via Twitter or Reddit or here on YouTube. So feel free to ask me and to show it to others that are also interested in linking space science with Python. Very well. I wish you a very nice rest weekend and happy coding, and I'm looking forward to hear from you. And until then, see you next week. Take care.